This is part 2 of Unit 1, Chapter 21. And in this part, we're going to be introducing a new concept of electric field. So where we left off was we looked at what charge was, okay? We looked at what happens when two charges are near each other and the forces that are exerted on one another due to the other. That's given by Coulomb's law, right? And we saw that opposites attract like repel, okay? We did some examples. We added some vectors together in example 21.4, right, where we had 3 charges and we were adding up the force Q1 on Q3 plus Q2 on Q3. And so now what we're going to do is we're going to still kind of talk about force, but we're going to talk about it in a roundabout way, if you will. I want to introduce the concept of the electric field. So every charged object produces an electric field in the same way that every object with mass produces a gravitational field, right? And what we know from experience is that only super duper massive objects produce a gravitational field with any real force to it, okay? For example, heavenly bodies, stars, planets, okay? Asteroids and things. Those really massive objects are going to produce gravitational fields. But for charges, even the tiniest charge produces an electric field that has some influence over other charged particles. So every charged object produces an electric field in the very same way that massive objects produce gravitational fields. So if that analogy helps you visualize electric fields, use it. It's nearly one-to-one analogy. So electric fields are vectors, and they exist at every point in space around a charged object. The magnitude of an electric field, well, it depends on the distance you are from the thing creating the field, which we'll call the source of the field, okay? The source of the field is a charged particle. So that magnitude is going to change, right? The magnitude of that electric field vector, it's going to change depending on how close or far away you are, right? You can see how the length of that vector is large when close to Q and smaller when farther away from Q. The other thing you may notice from these two images here is that electric field lines always point away from positive charges and toward negative charges, okay? This is the rule, this is the convention that has been established for hundreds of years, okay? This is the direction that electric field lines go just based on convention. So just as we do, with all physics, right, we're gonna talk about observations of this new concept of electric field, and then we'll get into the math, right, the quantitative aspects of it. So these are the basic observations of electric field, okay? So I kind of alluded to it earlier, right? How are electric field and electric force related? Well, they're definitely related, and they're related very straightforwardly by a factor of charge, okay? So let's talk about that. We know that all charges produce electric fields, okay? And that the direction of that electric field depends on the object sign, right, that's producing the charge. So in this case, we have object A. We have object A, okay, producing an electric field, and we've isolated just one field vector, okay? The field vector that exists right here. But in reality, there is an infinite number of field vectors, right? Long ones that start really close, short ones that start farther away, okay? There's infinite number of field lines, but we're just picking one. And at that location where we have this field line, we're going to bring in another charge, and we'll call him test charge Q0, okay? And he's going to be positive. So we're going to bring in that test charge Q naught, and we're going to put him right there where that electric field line originated, okay? And the relationship between the value of the electric field at that location and the force that Q naught feels at that location is basically this relationship right here, right? The electric field is the force scaled by the value of the test charge. Okay, so that's kind of a weird, way to express it. What we say is that, the electric field is a force per unit charge that object A exerts on a test charge at the location that we know the electric field, point P. Okay? So we're going to rearrange it in a minute on the next slide, and then I think it'll be more clear. So, right, in a sentence, if we want to talk about fields and forces and charges all in one sentence, what we say is that a test charge Q naught experiences an electric force F that is exerted by the electric field E created by A. Okay? So, right, we're not looking at Q naught's electric field. We don't care about Q naught's electric field. Okay? He's just a test charge. What we care about right now is the electric field created by object A. All right? It's very easy to get that confused because if we look at the next slide, right, let's map out the force vector and the electric field vector at the same time, right? You can see we wrote the force vector on top of Q, right? Because on top of Q naught. Because why? Q naught's feeling the force, okay? But the electric field vector is also written on top of Q naught, which is a little bit counterintuitive, right? Because you may be inclined to think that this E field vector belongs to Q naught, but it doesn't, right? This is big Q's E field vector, right? We're just there's a million of them, but we're just isolating the one that happens to be at the location that we put our test charge, okay? And so if our test charge is positive, you'll see that the electric field vector and the force vector are going to point in the same direction. And why is that? Well, the rules, right? The rules for E are that positive charges have field lines that point away, right? And negative charges have field lines that point toward the charge, creating the field. Okay, right? So we're using rule number 1 here for E. What's the rules for F? Right? Opposites attract like repel, right? So is that force vector following our rules that we know? It certainly is, right? Because big Q, the charge responsible for creating that E field, it's positive. Little q is positive, and so therefore the force vector is pointing directly away from big Q, right? Because little q does not want to be anywhere near him. So now let's look at another situation, right, where we have the charge creating the electric field positive again, but now our test charge is negative, and we're going to place it at the location that we know the electric field, okay? Well, guess what? The electric field is still pointing to the right because it's the electric field created by big Q, right, which is positive, so it's going to point to the right. It's going to follow this rule up here. What about the force? Well, the force it's now pointing in the other direction. Why? Because we're following this rule, right? Opposites attract, right? Opposite charges are attractive to each other. So the force vector is going to point directly towards big Q, right? The force that little q feels is going to be an attractive force, pulling it directly towards big Q. So, and that's, right, that's because of our rules. So let me draw Let me see if I can grab another color here. Right, let's look at the situation. What if our charge that's creating the field is negative, right? Let's kind of do this. What if the charge that the field is creating, that the charge is negative of the electric field that's being created, okay? Well, and we have our positive and our negative test charge just as we have here. What are going to be the field lines and the force lines? Okay. So, well, let's draw the electric field. Okay. What direction is the electric field pointing at the location of Q naught due to big Q? Okay. Well, big Q is negative. So the electric field vector at this location is going to point directly towards the negative. Okay, following this rule. What about the force? Well, let's look at this rule, right? Opposites attract, right? So the force vector is actually going to point, other way. Is there an undo? Here we go. Doesn't matter. Our force is actually going to also be pointing in the same direction because opposites attract. Okay, so you see we have two different rules going on, two different sets of rules, right? One for E, one for F. So now let's look at this situation, right? So negative Q, right? Big Q is negative, so the E field is still going to point to the left because of this rule. What about the force? Well, like charges repel, right? So little q naught is not going to want to be anywhere near big Q. They're both negative, so the force is going to point the opposite way. Okay, so those are the rules. And those are going to help you understand the relationship between F and E. So the other thing that you must remember, right, is who's creating this E field that we're drawing. Who's creating the E field? It's not the test charge. It's the big charge, okay? And so when you get these problems, think in your mind, okay, who's creating the field? Who's experiencing the field, okay? So that's how electric field and force are related. Let's look at some other qualitative observations of field lines before we get into the nitty-gritty math. So here we have two arrangements of charged particles, right? The arrangement on the left is a dipole, which is basically you have equal magnitude charges, different polarities separated by some distance. And you can see the electric field lines still leave, right? They exit positive, enter negative charges, okay? That's just the convention that we use. What else I want you to notice is, these electric field lines are all curved, right? As they go from one charge to another. But if you wanted to know the electric field value at a particular location on these lines, you would need the tangent, the value of the tangent vector to that line. And so that's what you see here, right? This is tangent to that line. This is tangent to that line, right? Tangent to that line. And you can see the magnitude of those E fields. Look how they relate to each other, right? Super steep, right? This is a steep ascent. Therefore, you're going to have a big positive E field, right? Here we have a kind of shallow descent, right? So we're going to have a tiny little, I covered it up in green, but a tiny little E field vector, right? And here, this is kind of halfway between, descent and ascent, right? So he's kind of a medium-sized vector. So these are electric field lines. These are all lines. To get the E field vector, you need the tangent to that line, okay? We're not going to be doing any problems. This is just, for your understanding. We're not going to do any problems like this. And so the other thing I want you to notice that you can kind of gather from this side here is when you have, any point charges next to each other, you'll never find intersecting field lines. So the field lines never intersect, and that's definitely showcased here on this side, right? You don't see any intersection going on. And that's kind of a mathematical, the reason for that, it's purely mathematical. It has to do with the fact that an electric field has a unique direction in every point in space. Okay, so I just want you to take that for granted, okay, if you're really interested in that. There's a lot of fun proofs that you can do to prove that. It's kind of like a mathematical thing. So if that's something you're interested in, you can ask me about it and I'll point you towards the rigorous math that supports that statement. But all you need to know is that field lines never intersect, okay? So let's talk quantitatively about the value of the electric field at a particular point in space. Okay, and so here we have the equation for the electric field due to a point charge. Okay, so, right, a point charge is emitting an electric field at every point in space, and we pick one point right here, and we want to know what's the field value right there, okay? So the field value is given by 1 over 4 pi epsilon naught, the value of the point charge creating the field, divided by r squared. What's r? R is the distance, right, from the charge creating the field to the place that we want to know where the field is, okay? Source and point, okay? So you're going to hear that terminology a lot. Source is going to be the source of the field, and then point is going to be the place that we want to know the value of the point charge, okay? So r is the distance from source to field point, okay? And then, so that's the magnitude of E, right? And then we have a direction, and the direction of E is in r hat. So you may not have ever heard of r hat. What's r hat? You know what I hat is, you know what j hat is, you know what k hat is. You may even know what s hat is, right? That's cylindrical coordinates. You may know what theta hat is, right? Those are all unit vectors. R hat is a unit vector as well. And R hat has a special meaning. It is the vector, the unit vector, that points from the source, right, which is the point charge. It points from the source to the field point, okay? So R hat points from the source to the field point. All right, that is always that's the direction of r hat. It points from source to field, okay? So r hat, though, does not have any ties to a coordinate system, right? R hat is simply the direction from source to field, okay? Direction from source to field point. So when we come up with an example or a homework problem, it'll be our job to translate r hat into proper coordinates, right? Whether it be Cartesian, cylindrical, whatever, right? But we're going to be mainly dealing with Cartesian. So I'm going to show you how to do that conversion, and then we're going to do an example, okay? So my slides, let me see if I can pull up, I have my slides a little bit. Let me go to the slide of past the example, and then we'll go back to the example, okay? I want to talk about r hat. What is r hat, right? R hat's a unit vector, and it represents a very common direction that is used in physics. And it's the direction from a source to a place that we want to know the value of the field that the source is creating. So, r hat does not have a coordinate system tied to it, and you choose what is appropriate for your problem. We're going to be doing lots of conversions into Cartesian, so I'm going to give you flat out here is, right, the conversion factor. If you want to know where that expression comes from, I outline that right here. So we know that any vector can be expressed in terms of magnitude and direction, so our vector, position vector from chapter 3, well, it can be expressed as magnitude of r in the r hat direction, okay? So we also know from chapter 3 that the position vector can be expressed in terms of Cartesian coordinates as x coordinate I hat, y coordinate j hat. We can set these two expressions equal to each other and solve for r hat. And that's how you get this guy right here, okay? So r hat is converted to Cartesian using that. And so what's r, right? What's r? What's little r? Remember, that's the magnitude of the r hat vector, but it's also the magnitude of this, right? So it's the distance from source to field point. And if your field point is xy, okay, somewhere up here, and your source is at the origin, r is just going to be that distance, which you can get from Pythagorean, okay? So now let's go back to our example. We're not going to do this example. We're going to do the one before it. Okay, and I have it, the way I have the example done is I have it in animations, but what I'll also do is I will upload a written version of this, okay? So let's go through it now with the animation. So basically, this is example 21.6 in your book, and what we're going to do is we're going to find the value of the electric field vector, right? So we need the magnitude and the direction of the electric field created by a point charge, right? A point charge of -8 nanocoulombs that's located at the origin. And we want to know the electric field vector at x equals 1.2 and y equals -1.6. So that's the fourth quadrant. Okay. Oops. Something has happened. I'm sorry. There we go. So the way I kind of did the animation, right, is I kind of selected portions of that problem-solving strategy just to kind of show you how you can use it to help you solve problems. So, right, we're going to find the vector. We're going to use this equation that we were introduced to, right? And we're going to build the vector. So the way we build vectors is, right, find the magnitude first, then the direction. So let's do that. Let's find the magnitude. Well, before we do that, let's draw the picture, right? If we're going to follow the problem-solving strategies, we have to draw our picture first. So, right, negative charge Q is at the origin. All right, place we want to know the field is down here in the fourth quadrant. And right off the bat, we can draw the direction of the electric field vector using the rules, right? The rules being electric field vectors point from or point toward negative charges, right? So the electric field vector at point P is going to point directly towards, right? If I draw a straight line between the two, electric field vector is going to point directly towards the negative charge at the location of P, right? Because that's where we want to know the E field vector. So we already know, I mean, we kind of know the answer. We just need the quantitative part of the answer, right? So let's do that. Some things to recall, right? The E field, well, I already mentioned it. I forgot that I had this here, right? The E field points towards negative charges, right? So your electric field is going to point directly towards negative charge. And the unit vector r hat, right? The unit vector r hat always points in this direction. But is that the direction of E? No, right? E is actually pointing this way. So E is actually in the negative r hat direction, right? So just think about that. E is actually in the negative r hat direction. So when it's time to assemble our vector, we need to take that into consideration. Okay, and there's a couple ways to do that, and we'll talk about both ways. So there's little pop-ups that kind of just what I already talked about, right? This vector right here, that's the position vector, and that represents your location in the Cartesian coordinate system from the origin, right? And that's what we're using as our conversion factor, basically, to convert from r hat to I and j hat. So let's do it. Let's build our vector here. So there's a little hat missing there, right? Let's get our magnitude. Plug our numbers in. Okay. What's r, right? R is the distance from the source to the field. So that's going to be the hypotenuse of this triangle right here. So we can use Pythagorean theorem to get the length, which is 2 meters. And then we can do our conversion factor, right? Because here we got this part all nailed down, right? That's going to be a value that we can easily calculate. What about r hat? So let's convert r hat into I and j hat. So let's use our conversion factor. Plug in our x and our y coordinates. Plug in r, which is 2. And your result is going to be what r hat is, right? Positive r hat. Our result is going to be positive r hat, which is basically it tells you, right, these are the conversion factors that's going to scale our unit vectors I and j hat, okay? You can't just go straight from r hat to I and j hat, right? They're going to be scaled because unit vectors always have a magnitude equal to 1. So if I were to find the magnitude of r hat, it would need to equal 1. So if I find the magnitude of this, it should equal 1, right? Because it's directly equal to r hat. So this is our r hat vector right here. And then we have our magnitude calculated. So let's assemble those two pieces together. Sorry, I think it got repeated here somehow. There we go. So let's fix that. We should have some parentheses here, right? Here's our magnitude. Here's our direction. All right. You'll notice that what I did was put r hat directly in here. And I let my negative sign hang out with q. All right. I didn't do double negative, right? I know E vector was pointing in the negative r hat direction. So what I could do is I could have left my negative with r hat and reported this as positive. And why that's okay mathematically is because when you assemble a vector, this part is always positive, right? This is the magnitude, and then you let the direction give you a negative sign if necessary. Here you can do it both ways because, right, it's just a negative sign. And if there's only one of them, it's going to be distributed correctly. If you put two negative signs, if you put a negative here and then you also report this as negative, you're going to get the wrong answer, right? Because you're adding two negatives in when there should only be one. So it's up to you how you want to do it. I'm going to post the two different ways so that you can see, but just keep track of your negatives. Either do magnitude, always positive, direction negative. You're going to have to remember that r hat is the E field is going to be in the negative r hat direction because Q is negative, right? So your negative sign would go there. Or, right, you just remember that Q is negative, so let me leave my r hat positive. Either way it works. There's only one negative flying around. And so then there's our final answer, okay? You can see how it changed sign, right, because of that negative sign. So our E field vector is going to point, right, in the negative x direction, positive y direction, which makes perfect sense with our picture, right? E field was going this way, which is negative x, positive y. So there's your check, right? Magnitudes are easy to calculate. Directions are going to be the hard part. So if you got the magnitude down, you look at your picture and then you make sure you have the right signs, okay? That's where the physics and math kind of differ, right? Because sometimes when you're doing, I don't know if you've ever got into vector calculus or even in Calc 3, you do a bunch of math and you don't really have a way to check yourself, right? Here you have physical rules. This is why physics is so awesome, because you have physical rules. For example, the rules being electric field lines point towards negative charges, right? You have physical rules that help you check your answer, okay? So there's our physical rules. We already know by observation that E field lines point towards negative charges. So my E field vector better have a negative x direction and a positive y direction, okay? That's how you check it. So, so then we talked about what r hat is. Take some time to kind of go over it and look at some other resources of what r hat is, just to make sure that's fully kind of cemented in your head. And I'm going to skip this example. And I'm going to break and create another video. This is going to be the beginning of part 3, okay? So this is the end of part 2. We did one example. We talked about electric fields. Part 3, I'm going to talk about how to find the electric field due to multiple point charges, okay? A continuous distribution of charge. We're going to do a really big example that involves integration, changing variables. So I want to put that as a separate video, okay?